I've been discussing with you the difference between covalent or molecular compounds and ionic compounds. We're going to learn how to name these things. Well, we'll learn how to name these pretty exhaustively. This will just learn how to name some of them. We're not going to get real exhaustive into this, but nevertheless, we want to be able to especially name the ionic compounds and have some familiarity with naming these. So we first are going to have to recognize before we do this that there are two completely different ways of naming these. There are two completely different naming systems. So when you encounter a compound and you need to name it, you should recognize that the first thing that you're going to want to do is determine which it is, so that you use the correct naming system. And the simplest way to do this is to just check to see if it has a metal in it. I don't remember if we've talked about what a metal and a non-metal is, but if we haven't, let's refresh our memory. If we go to the periodic table and you look at the periodic table, you're going to see over on the right-hand side, you're going to see a stair step, kind of like this. And compounds to the left of the stair step, those are going to be the metals. And most compounds in the periodic table are metals. To the right of the stair step, that's going to be where the nonmetals are. And your covalent compounds, those tend to form by nonmetals combining with nonmetals. The ionic compounds, those are formed by metals and nonmetals combining. So, if you see a metal, very often, and for this class, this is what we're going to use, if you see a metal, you know it's ionic. So instead of writing this, I'll say contains a metal. There is a very important exception to this rule that I want to write in. It either contains a metal or there just happens to be this one ion that forms and it doesn't contain any metals, but because it's an ion, it makes ionic compounds. And we'll talk more about this later, but there's this ion called the ammonium ion, and it looks like this. So if I see NH4 in a particular compound, like ammonium chloride, I see that NH4, when I see that ammonium, that triggers in my head that I've got an ionic compound. Covalent compounds, they're going to be nonmetals. There are exceptions to this, but unless you take some advanced chemistry, we're not going to worry about that. These will be the rules that we're going to use for this particular course. Now remember, there are different naming systems for covalent compounds and ionic compounds. We're going to focus first on the covalent naming system. And actually, we're only going to name a certain type of covalent compounds. I'm not going to worry about all of them. And this is called a binary covalent compound. This is all we're worrying about. A binary covalent compound is a covalent compound. Well, of course it's covalent. I'll better write it in. A covalent compound made of only two types. Of atoms. You already know what one binary covalent compound is. It's H2O. It's made of two types of atoms, hydrogen atoms and oxygen atoms. So the binary means how many different types of atoms are in the covalent compound. With water, hydrogen atoms, oxygen atoms, two types of atoms, binary covalent. And here's the naming system. And I'm right here on, what am I on? Slide number 7. So there's going to be these prefixes we got to remember that indicate number. And so here what we do is we first write the prefix that tells us the number of atom 1. Except we don't use mono. No mono here. isn't going to make sense at first, but we'll do some examples and it should make sense. Then after denoting the prefix, except for mono, you just say the name of the first atom. And then you do it again. What's the prefix for the second atom? Prefix of second atom. Prefix number, so how many there are. So like here, for water, we'd have to need some prefix telling us 2. And then we need some prefix telling us 1. And then finally, the caboose, we name the second atom with an IDE ending. So to give you an idea of what I'm talking about, naming atoms with an IDE ending. Hydrogen with an IDE ending is hydride. Oxygen with an IDE ending is oxide. Nitrogen with an IDE ending is nitride. Well, we better tell you the prefixes. Those prefixes are listed on slide 7. I'm going to write them right here. The prefix for 1 is mono. The prefix for 2 is di. The prefix for 3 is tri. The prefix for 4 sounds a little bit like tetras. You know, the four squared shapes that fall in the game of Tetris. I don't know, does your generation play Tetris? I don't know. If not, look it up. It's a fun game. The prefix for 5 is penta. The prefix for 6 is hexa. These probably sound familiar. The prefix for 7 is hepta. The prefix for 8 is octa. The prefix for 9 is deca. And the prefix for 10, prefix for 9 is nona. And the prefix for 10 is deca, like decade or decathlon, octagon. Those should make sense. Okay, so let's apply this rule. We're going to call this water, but let's just apply this rule as if we were going to name water using the binary covalent compound system. So the first thing I need to do is write the prefix showing me the number of atom 1. There's 2 hydrogens, so I need to write down di. Di, name the first atom, hydrogen. Prefix showing the number of second atom. Well, there's 1, which is mono. And then I need to name the second atom with an IDE ending, oxide. So if I were being strict about this, we'd call this dihydrogen monooxide. But what people really do, if there's like 2 O's like this, you just drop one of them. And you would call this compound dihydrogen monoxide, would be the name for it. And if you get some time, I'd like you to Google dihydrogen monoxide and search around the internet a little bit. You might find something humorous. Let's try another one. Anybody know what this molecule is? What do we call that? We call that carbon dioxide. Naturally, that's what we call it. But actually, calling this carbon dioxide fits the naming system. I'll show you how. All right, let's go for it. The first thing we need to do is write the prefix showing the number of the first atom. But you don't use mono here. So even though I do have 1 carbon atom, which uses the mono prefix, we never start with saying a compound with mono. So I'm not going to have mono something. So we skip the mono here. I write the name of the first atom, carbon. Prefix showing the number of the second atom, 2 is di. Name of the second atom with an IDE ending, oxide, carbon dioxide. I'm going to give you one to try on your own, and we'll pause the video and then I'll write the answer for you. Let's do this one. P2O5. And that we should call diphosphorus pentoxide. We also want to be able to do this in reverse. So you want to be able to take a name and be able to write the formula for it. So let's try that. So you want to be able to be fluent and go both ways. So let's see. Let's do, what can I have here? Carbon tetrachloride. Well, I just got a name. I don't have a prefix here. That should tell me I just have one, right? There's no prefix. That's going to tell me I'm going to have one carbon. And then chloride, that's going to be chlorine, and I'm going to have 4 of them. So in this case, I've gone from the name back to the formula for the particular compound that we're talking about. You should be able to do that as well. If you look at slide number 9 on your PowerPoint, there's some practice for you to do. You might want to do that and make sure you know what you're doing. Okay, now the tough one. All right, we've gone over how to name a certain type, a simple type of covalent compounds. Now we're going to get into the detail, the dirty work of learning how to name ionic compounds, and we're going to do this, there's a lot of detail here that we're going to go into. Okay, so it sounds very easy, and in a sense it is, as long as you've done your due diligence and you've done a lot of studying and memorization is what this is going to take. But if we're going to name an ionic compound, first we want to identify it as ionic, and the way you can tell it's ionic is if it has a metal or if it has the ammonium ion. We've covered that before. But if I want to name it, all you got to do is just name the cation and then you name the anion. That's it. Sounds simple. But it can get tricky. And let's just remember what a cation is. A cation is a positive ion. Remember that? That's how I write the word cation with a plus there to remind me that a cation is a positive ion. And the word anion reminds me there's a mnemonic right in the word, and anion is a negative ion. So how do we name the cation? How do we name the anion? Okay, so let's go naming cations first. There are different types of ions. There are ions that we call monoatomic. They're made of one, they come from, I should say, one atom. Let's see, monoatomic. One atomed, that's terrible, ions that come from one atom. And these are pretty easy. You just got to look at the periodic table to figure these out and know a few tricks there. There are also these things called polyatomic ions. And poly means many, so you can probably guess that a polyatomic ion is an ion that comes from more than one atom. So I've mentioned the ammonium ion. I want to just talk about that a little bit to give you an idea of what a polyatomic ion is. I'm going to draw the structural formula for the ammonium ion. So it's like this packet, so to speak. So you get a nitrogen atom that's connected to 4 hydrogen atoms. And this is done in a manner where if you do this whole thing, it's got a +1 charge. So it's an ion packet. It's kind of like it's kind of like a little molecular. It's like a molecule with a charge, I guess is the best way to describe it. And part of your success in chemistry is going to be based upon your ability to know these things, to know what the polyatomic ions are, to sort of know how they behave, and to memorize their names, and to memorize their formulas, and to memorize their charges. If you take the time to really dig into this and become fluent in polyatomic ions, and recognizing, seeing them when you see, say, a compound, it's really going to help you throughout this course. Understanding these polyatomic ions, having them memorized, but not just memorized, but being fluent in being able to recognize them, know what their charges are, know what their formulas are, is going to become very important. And you will hear me say this again. Memorize your polyatomic ions, and I have these listed. The list of polyatomic ions that you should memorize is on slide 15 of the PowerPoint. There's a whole bunch of them listed there, and I'll cover them again in a bit. But for now, I'm just giving you an overview of how we're going to name our polyatomic ions and our cations. Okay. So really, there's only one cation, so we're all the way back to naming cations. So if I'm going to name a monoatomic ion, for example, sodium, that one's easy. We just call it the sodium ion. If I see this, I call that the calcium ion. And there's only one polyatomic ion that's positive that we're going to need to remember. That's this. If I see that, I'm going to call that the ammonium ion. We just named the cation. There are also monoatomic ions that have possible multiple charges. So, monoatomic ions that have multiple charges Let me give you an example. Copper. Copper ions, they can be this or this. So you can have a copper ion that has a +2 charge, and you can also have a copper ion that has a +1 charge. This one tends to form blue-green compounds. This one tends to form orange, red, or brown compounds. So I can't call this the copper ion and this the copper ion because that's ambiguous. They're different. So how do we distinguish between these? Well, what we do, I hope this makes sense. I mean, it may not make sense why we did it this way, but at least it makes sense that this is called the copper 2 ion, and this is called the copper 1 ion. Iron's another substance, another thing that can form multiple charges. We call this the iron 2 ion, and we call this the iron 3 ion. That's what we say. What we write this as iron, and in parentheses after it, we put the Roman numeral 2. For this, we write iron 3. For this, we write copper 1. For this, we'd write titanium 4. Okay, So now we're going to try to dig in and talk about how we can tell what charge something will have. There's some of this that if you just understand some concepts, memorizing what needs to be memorized is quite easy. There's other stuff that you're just going to have to dig in and memorize. We'll start with the easy stuff first. So let's go to slide 11 on your PowerPoint. We're going to learn how to sort of name the monoatomic ions, the ones that just come from one atom. And what I'd like you to do is I'd like you to look at the first column in the periodic table, which you'll see this. Sodium, potassium, rubidium, cesium, francium. So these are the alkali metals. Now all of these you should recognize they want to lose one electron. Did we talk about losers to the left and receivers to the right?
Not sure.
Not sure if we did. Well, let me talk about it. I can't remember. Forgive me if we already talked about it, but you might remember, if not, don't worry about it, that we recognize that it's the noble gases. That's the family all the way over on the right-hand side of the chart. Helium, neon, argon, krypton, xenon, radon. These noble gases, they have we'll call it a magic number of electrons. Helium has 2, neon has 10, argon has 18, krypton has 36. This is a magic number of electrons that all atoms sort of want to achieve. And they do this by gaining or losing electrons. That's the way it works. That's how chemistry happens, actually. When atoms trade electrons or share electrons or gain them or lose them, that's when actually the atoms can combine and form compounds. And that's when chemistry happens. So if we look at lithium and sodium and potassium and rubidium and cesium and francium, it says 3, 11, 19. I'm trying to forget what these, I think this one's 87. What are the other ones? Oh, it's hard to see. Hold on. There we go. 37, 55. These numbers up here, remember that tells us how many protons are in the nucleus. It also tells us how many electrons the neutral atom has. If we go all the way across the other side of the table, we got helium with 2, we got neon with 10, we've got argon with 18, we got krypton with 36. What else is going to be? Krypton, xenon, that's going to be 54, and we got radon with 86. These noble gases are completely stable. They don't react, well, they do, but helium and neon have never been observed to react with anything to form a stable compound. So what that means is they don't want to change the number of electrons they have, is what it means. And so there's something magical, we'll call it. We don't like to use that word in science, but for here we'll just use it so you kind of understand the idea. There's something magical about these numbers of electrons that atoms sort of want to get to this number. And so lithium, a lithium atom, wants to get down to 2 electrons. So that's easy to do. It's just got to lose 1 electron. Watch this. So if I take a lithium atom, it's got 3 electrons. If it loses 1 of those electrons, so it gets rid of it, that's not going to just disappear into the void. It's going to go somewhere else. Electrons always have to come from and go to somewhere. But if it gets rid of this electron, it'll go from having 3 electrons to 2 electrons, and it'll be happy. I like to call this chemical heaven or chemical nirvana. This is where all atoms want to be. But notice, if it loses an electron, losing an electron is a positive thing. The electron has been lost. And we always are going to watch, when I write an equation like this, the charges, if we add them up on one side of the equation, have to equal the charges on the other side of the equation. There's a law of conservation of charge. And so this positive and this negative, that's -1 and +1, that makes 0. And that's 0. That's the charge over here. So a lithium atom loses 1 electron to feel like helium. And when it does so, it gets a positive 1 charge. And it should make sense to you that every single one of the alkali metals does the same thing, right? If this loses 1 electron, it gets to 10. If potassium loses 1 electron, it gets to 18. If rubidium loses 1 electron, it gets to 36. So all of the alkali metals, every single one of them, when they form ions, which they readily do because they want to get here, they form +1 ions. So lithium, sodium, potassium, rubidium, cesium, and francium, when they form ions, they always form +1 ions. All alkali metals form +1 ions. So by understanding this idea, we can look at the periodic table and we already know if I see, for example, lithium in a ionic compound, it's going to be a +1 charge. That's what it does. I can put sodium here, same way. Sodium in an ionic compound, +1 charge. That's it. That's all they do. That's all the alkali metals do. Now let's move 1 column over. We're going to go to the alkaline earth metals. So that's beryllium, magnesium, calcium, strontium, barium, and radium. What kind of ions do you think the alkaline earth metals, like calcium, what does that form? What kind of charge does it form when it makes an ion? Let's think about that. Look at calcium. Calcium's atomic number is 20. That tells us how many protons it has in its nucleus. It also tells us how many electrons it has if it's neutral. So a calcium atom has 20 electrons. What does it want to do? It wants to get to chemical heaven. It can do that pretty easily, get here like argon, by losing 2 electrons. So let's just write the process here. Calcium goes to some form of calcium and 2 electrons. Well, let's see, I got 2 negative charges. I better put a positive 2 charge here so that I end up with 0 net charge over here and 0 net charge over here. Calcium and all of the other elements in that second column, they all form +2 ions. Beryllium +2, calcium +2, magnesium +2, strontium +2. So recognizing that first column, they're all +1 ions. The second column, those are all +2 ions. So by looking at the periodic table, we can have this memorized. Now the ones in the middle, the transition elements, we're going to ignore them for now because these are these elements that can often have multiple charges. We're going to just try to memorize a few of those, but we're going to skip them from now. Let's go all the way over to the other side of the periodic table, right here next to the noble gases. You'll see, what's this, fluorine here, chlorine, bromine, iodine, and then astatine. What do you think a fluorine atom wants to do? It has 9 electrons. Think it wants to gain or lose an electron. It wants to gain 1. Because if it gains 1, it goes from 9 to 10. What happens if a fluorine atom gains an electron? In that case, it's going to have to become negative, isn't it? And that's what all of these atoms do. The fluorine atom gains 1 electron to make it feel like it has 10. And what we say is that the fluorine atom becomes the fluoride ion. So the anions, when they gain an electron, they then get an IDE ending when we say its name. So the sodium atom becomes the sodium ion. The cation's name stays the same. The fluorine atom gains an electron and becomes the fluoride ion. So the anions get this IDE ending. All of the halogens, They're all -1 ions when they form ions. What about oxygen's group? I think I have that right. Yep, and polonium. What kind of ion do you think oxygen forms to form the oxide ion? I hope you're saying it's -2. It's -2. So the oxide ion, the sulfide ion, the selenide ion, the telluride ion, well, the polonide ion, I've never heard of that in a compound, but nevertheless, these particular atoms, when they form a monoatomic ion, they all go -2. Probably won't come as a surprise to you that nitrogen forms a -3. And you should probably remember, this won't come as a surprise to you either, that aluminum forms a +3 ion. And all of this is indicated on the periodic table that is on slide 11 of your PowerPoint. You'll see an arrow going down that first column, +1, +2, I like to say +1, +2, skip a few, +3 for aluminum, -3 for nitrogen, so nitrogen becomes the nitride ion, and phosphorus right below it becomes the phosphide ion when those form ions. And then we have -2, -1. And one way I like to mention this, if I haven't mentioned it before, is you'll notice that on the left side of the periodic table, we have the metals that lose electrons. So I like to say the losers to the left. And over here on this side of the periodic table, we have the nonmetals. Those gain electrons, and they're on the right. So I like to say receivers to the right. Losers to the left, receivers to the right. Of course, except the noble gases, they're in heaven. They don't worry about gaining and losing electrons. So we've just gone over how to name a monoatomic ion that always has the same charge. So your first column, the alkali metals, those are always going to be +1. The alkaline earth metals, when they go to ions, it's always going to be +2. Oxygen's group is always going to be -2. And the halogens, those are always going to be -1. There's also the case of some elements that can form ions of more than one charge. And if you will, go to slide 13 on your PowerPoint. On that slide, there are a list of some elements that can form ions with more than one charge. And if you go to that slide 13, you'll see some of them highlighted in red. And the ones that are highlighted in red are the ones that I'm going to expect you to know. I don't know how to tell you how to memorize this other than to memorize it. So if you look, chromium can form a +2, a +3, or a +6 ion. And those would be called the chromium 2, the chromium 3, and the chromium 6 ions. You'll notice manganese, manganese shows a whole bunch of different charges, +2, +3, +4, +5, and +6. Iron can form +2 or +3. Copper, as I mentioned before, can form +1 or +2. Tin, that's one that you should remember. Tin can be +2 or +4. I'm going to skip mercury for a second because I am going to talk about that one, but let's go to lead. Lead can form +2 or +4. Now let's talk about mercury. And I'm going to contrast that to copper. So let's just write, that's copper 1. That's copper 2. And I would write this as copper 1. And I'd write this as copper 2. Okay? Now this gets goofy with mercury. Mercury, oh boy, this one's called mercury 1. What the heck is going on here? And this one is called mercury 2. What in the world is happening here? Let's let's talk about it. Up to this point, with these transition elements, so notice all these are transition elements, they're in the middle. Well, lead's not one, but nevertheless the rest of them are. But these elements that form ions with different charges so far, except for this one, are all monoatomic ions. They're ions that came from one atom. In this case, though, we've got a polyatomic ion. Let me show you the way this one's made. This is seen to happen as a Mercury 1 and a second Mercury 1 connected together. So you have two Mercury 1 ions that travel together in a packet. They're connected together. They move. So because I have two Mercury 1 ions connected, the thing is going to have a +1 charge. Excuse me, back that up. Because I have two Mercury 1 ions connected together, overall that's going to show a +2 charge, right? I got a +1 and a +1. Overall that makes a +2. But it goes together, so I've got the +2 charge, but because it's made of two Mercury 1 ions, we call it Mercury 1. So this is a polyatomic ion. All the other ones are not. Now I'll contrast it with this one. This comes from a single mercury atom that has a +2 charge, so we just call that one Mercury 2. Okay. If you look at slide 14, there are two transition elements that always form the same charge. That's going to be zinc. That's atomic number 30. Zinc is always a +2. That's it. So when I say the zinc ion, you should know that's a +2. I don't have to say zinc 1. I don't have to say zinc 2, because zinc is always a +2. If I say zinc ion, we just know it's +2. Silver is the same way. The silver atom, which is atomic number 47, it only forms a +1 ion. So the silver ion is Ag +1. I don't call that silver 1. I don't call it the silver 1 ion, because when silver forms an ion, it always happens to be +1. Okay. And now we finally move to the polyatomic ions. Just before I do that, I want to kind of back up and show the overall picture here. The overall picture is we're trying to name ionic compounds. And to do this, you say the name of the positive ion, and then you name the negative ion. So really, all I'm doing is I'm trying to go over this process of naming all these different ions, so that when I see a compound, I know, okay, this is how I name the cation, this is how I name the anion. So if I know that, I can name any ionic compound that I see. So on slide 15, I've mentioned this before, you're going to see a list of polyatomic ions. It's going to be very wise for you to memorize this list. In other words, carbonate. Is that listed right? It is. I've got this, I've been doing this 20, 30 years, so I'm just fluent in this, and I'm hoping that you also will take the time to get as fluent as possible as you can with these. But when I hear carbonate, I immediately know that. So when I hear carbonate, I know that the carbonate ion is comprised of a single carbon atom and 3 oxygen atoms connected in some way. We'll learn about that later in the course, how they're actually connected. But when they do this, the overall thing has a -2 charge. And that's how all of these should be viewed. So there's a list here that you should memorize. I'm going to take a little time to talk about some tricks that you can use to help you memorize these. So let's start with, let's see if we can do, yeah, let's do this for example. This one is called the sulfite ion. This one's called the sulfate ion. And then this, what's that called? Well, that's the sulfide ion. Wow. I mean, look, there's only one letter difference. A D versus a T, and you've got to know. You've got to know. When I hear sulfide, this is what I'm talking about. When I hear sulfite, this is what I'm talking about. Now, this is a monoatomic ion, so we know that from looking at the periodic table what its charge should be. These are going to need to be memorized. But one thing that you can do is you can recognize when you see a group of ions, polyatomic ions that have a particular nonmetal that are bonded to different numbers of oxygen, the lower of the two is going to have an ITE ending, and the higher of the two is going to have an ATE ending. So, for example, there's two different forms of polyatomic ions with oxygen bonding to nitrogen. In this case, we're going to call it nitrite, the smaller number of oxygens. And in this case, we're going to call it nitrate. And there are many pairs like this. There's phosphate, PO4, 3 minus. That's phosphate. This one happens to be phosphite. I don't have you worry about that one because we never see it. We just worry about phosphate. But doggone it, there's this one. Of course, there's always got to be an exception. There's this one element, chlorine, that bonds to oxygen to form polyatomic ions in 4 different ways. So let's go over that particular one. It can be ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Well, this 8-ite alone isn't going to work for this. So what they do is they'll just start with this pair first. So we start with this pair. We're going to call this one chlor 8 because it's the higher of the two. And we'll call this one chlorite because it's the lower of the two. Well, we're going to go even lower than chlorite, and there's this Greek prefix, hypo. Hypo means low. So we're going to call this one lower than chlorite. We're going to call it hypochlorite. There's another Greek prefix that I'm sure you're familiar with, hyper. That means above or higher than. So you'd think we'd call this hyperchlorite. Hyperchlorate, because it's higher than chlorate. But we drop the high and we call it perchlorate. You don't have to use these little tricks to help you memorize them. I just like to point them out to show that, while it looks like there's just a bunch of jumble in the names, there is sort of a system to it, although it's not a perfect system. There's a system to it that if you hear it, you can kind of remember some of these a little better. There's another way that we can look at some of these that might help you recognize the names. For example, let's take sulfate and let's take sulfite. And many times, the only difference between a polyatomic ion and another one is the addition of an H+. So if I take an H+ and I add it to this, what I'll get is HSO4 minus. This happens a lot. And if I take an H+ and add it to this, I get HSO3 minus. Notice when I add an H+, the charge goes up one, right? It goes up from negative, and we have to add the hydrogen. So this is called sulfite, and this is called hydrogen sulfite. And sometimes, in the olden days, instead of saying hydrogen, they used to just say bi. So this can also be known as bisulfite. This here, well, this is sulfate. So we're going to call this either hydrogen sulfate or bisulfate. And that may help you work through memorizing quite a bit of the polyatomic ions that are listed on slide number 15. Okay, we're finally at the point where we can name some ionic compounds. Let's try it. So I'm on slide 17 on the PowerPoint. Actually, do I want to go to this one? Yeah, actually, before we do that, I'm going to go to slide 18 first, okay? Slide 18 first. I'm going to just draw a couple here. Na2O. We'll also try this one. AlNO3. Let me just name these two, and then we'll go to writing the formula if you're given a name. So this is pretty easy here. I mean, naming ionic compounds is really easy. First thing I want to do is I want to look at this and I want to say, is this ionic or covalent? It's ionic because it contains the metal sodium. And if it's ionic, it's easy. I'm just going to name the metal, I'm going to name the cation, which is sodium, and then I'll name the nonmetal, which is oxide. So this appropriately is named sodium oxide. That's the correct name. Now I'm going to point out what a lot of students do who don't study this stuff enough. A lot of students who don't study this enough, they don't take the time to recognize that there are two completely different naming systems. One for molecular compounds and one for ionic compounds. The students who don't remember this, they'll use the covalent naming system to name this, and if they do that, they'll call this disodium monoxide, which is incorrect, because they used the incorrect naming system. And you're going to have to keep it straight. You're going to have to make sure that you understand there's two different naming systems for naming binary covalent compounds and ionic compounds. Got to get that straight. You got to recognize if I see a metal or the ammonium ion, it's ionic, and then it's easy. Name the cation, name the anion. In this case, well, it's going to be the aluminum ion. And because I have my polyatomic ions memorized, I easily recognize that as the nitrate ion. So this would be called aluminum nitrate. The naming system for ionic compounds is you name the cation and you name the anion. And if you have your polyatomic ions memorized, naming something like this is quite easy. If you don't have it memorized, you're going to call this something like, I've seen this kind of thing, sodium nitrogen trioxide. You see people do that because they haven't taken the time to memorize the polyatomic ions. Okay, I'll let you do the others for practice. We're going to go back to slide 17, and we're going to go over writing the formulas for ionic compounds if we're given the name. Now this requires some work. So we'll start with some easy examples, and then we'll move to more difficult ones. We'll try to work through maybe 5 of them, I think. So we'll do sodium bromide. Let's try iron 3 sulfate. Save that one for a little later. Let's do calcium hydroxide. aluminum oxide. And we'll do potassium phosphate. And there'll be some others for you to, try on your own. And I'm going to do them in the order. Let's see, we'll do that one first. Probably be good to do this one second. Probably going to do this one third, fourth, fifth. Okay. So I need to write the formula for sodium bromide given the name. So I recognize it as an ionic compound. And so I'm going to need to write the symbol and charge of the sodium ion, which is Na+. Now, how do I know that? I know that because sodium is in the alkali metals. All alkali metals, remember, they lose one electron to become like the noble gas, and there's noble gas in terms of number of electrons. And when you lose that electron, you become positive. Bromide, that's a halogen, that's right next to the noble gases on the other side. Those all want to gain one electron. And when they do, they gain a negative charge. Now, in these ionic compounds that form, it must be the case that the total charge from the cations has to equal the total charge on the anions. And if that happens, you're good. And in this case, we're good, right? You got a single sodium with a positive 1. You got a single bromide with a negative 1. They match. And so we're done. The way we'd write the formula for sodium bromide is NaBr. That one's simple. They don't always work out that way, which we'll show you in this case. Aluminum oxide. So what I'll do here is I will write the symbol and charge for the aluminum ion, which is Al3+, and I'll write the symbol and charge for the oxide ion, which is O2-. Those don't match. I've got a +3 and a -2. We've got to get these charges to balance. One quick way of doing this that works often, but not all the time, with these substances is you just do what we call crisscrossing the charges. So in other words, I just take this 2 and stick it down here, and this 3 and stick it down here, and I've just written the formula for the compound appropriately for aluminum oxide. It's Al2O3. Now, why does that work? Let's talk about that. We'll write Al2O3 off to the side here. And what this is telling me is that if I take 2 aluminum ions, and 3 oxide ions, the charges should balance. Let's see. Let's say I got an aluminum with a 3+, and I need 2 of them. Well, if I have 2 3 positives, that's a total of 6 positive. Let's do the same thing with oxygen. -2, and I need 3 of them. Hey, look at that. If I take 3 2 negatives, I've got a 6 negative. Those charges balance, and we're good. So this would be the formula for aluminum oxide. All right, looks like we're doing calcium hydroxide. I know the symbol and charge of the calcium ion. I have my polyatomic ions memorized, so I know hydroxide is OH negative. Hydroxide is an ion that you're going to want to remember for acid-base chemistry. This is extremely important in acid-base chemistry. Now those don't balance. I've got a +2 and a -1. How many hydroxides am I going to need? I'm going to need 2 of them, right? If I get 2 of these, then I'm good. Now you got to be careful here. I don't want to write the formula for this like that. Because what this signifies is that I have in the compound 1 calcium, 1 oxygen, and 2 hydrogens. But you should recognize that if I need 2 hydroxides, I'm going to need 2 oxygens. So I could write it like this, but we don't do that. Why don't we do that? Because we want people to recognize that there's a hydroxide here, and we think of hydroxide as this OH together. So we want to kind of keep it together like that to say to people, hey, there's a hydroxide here. So here's the way it's done. Instead of writing it like this, we say, well, I'm going to take a calcium, and I want to keep that hydroxide like that. I want people to recognize that this is a hydroxide ion. And so what I'll do is I'll put a little subscript down here, and that little subscript says, you take everything that's in the parentheses and multiply it by 2. So I'm going to have I'm going to have 2 oxygens, I'm going to have 2 hydrogens, and I'm also going to have 2 negative charges. It's going to balance the +2 on the calcium 2+. Potassium phosphate. The symbol in charge of potassium is that. The symbol in charge of phosphate is this. I know that because I have my polyatomic ions memorized. This one's actually kind of easy. I hope you see you need 3 potassium ions to balance this. So I would write the formula for this as K3PO4. And then finally, iron 3 sulfate. Well, the symbol in charge of iron 3 is that. The symbol in charge of the sulfate ion, because I have it memorized, is that. Kind of like what we did with aluminum oxide. I hope you see we're going to need 2 of these and 3 of these. But we got to be careful here. Let's see. I can put a 2 down here for iron, but I can't just do this for my sulfate because that's going to make it look like I have 43 oxygens, and that's not what we have. What we have is 3 sulfates. And so again, we want to tell people, look, there's a sulfate here, and we do that by keeping all this together and saying we're going to multiply everything in the parentheses by 3. That includes the sulfur and the 4 oxygens. So in this case, total, we'd have 2 irons in the compound, we'd have 3 sulfurs in the compound, and notice we're going to have 12 oxygens. 3 times 4 is going to be 12. Get some practice. That's a lot of stuff, man.